Okay, in the last two videos, we have learned how to create a 3D cavity, right? If you remember, the outer shell is actually superconductor or perfect metal. And then we have two ports, port 1 and port 2, and it is have this superconductor or perfect metal, and then with this vacuum cutting a hole through this cavity. And inside the cavity, we also have inserted this one, which is the let me see that the object sapphire, right? On top of which we had also put a Transmon qubit. And this Transmon qubit basically is that we have a two superconducting metal, and then in the middle we just add the model for a Josephson junction. HFSS cannot model Josephson junction, right? But what we care about is in this study is the inductance due to the large inductance due to the Josephson junction, right? We know that Josephson junction can act as a nonlinear inductor, and it creates a very large inductance. And in order to simulate this, what we have done was to put the lump boundary to it. And if we double click on this, you see that we assign Lj nanohenry to it. And this Lj is actually, if you go to this design properties, the Lj that we have put in is 5 nanohenry. I put it smaller so that I can have a large cross-Kerr, but you will see that later, right? Another important thing is that we deliberately put a 9 here, not this arrow, but this 9, right? This is poly 1. This not poly 9, poly 9 1. This is not important for the simulation. However, later when we do the energy calculation, we use this 9 to do the integration. So we put it there. Now this is completely independent from the metal, Qiskit Metal, right? And by the way, I have two projects. The first project was just the cheat sheet that I used to to check the dimension when I create this final project. The project I really have is this Eigenmode Simulation. Okay, so now we will try to do the analysis. Let's not do Qiskit Metal yet, just HFSS itself, right? What does it do, right? So I am going to right click and then say add solution setup. For example, I can say I want to simulate 3 modes, right? For now, I do 3 modes. At minimum frequency, I start with 1 gigahertz. And I allow it to have, let's say, 8 passes, right? This is a demo. I don't want to spend too much time, right? But I say, okay, let's wait until the delta frequency is within 1% between each passes, right? For example, if you finish, it only have 1% change from the 5th to the 6th pass, then you will just stop. And usually we only need to converge on the real frequency, right? No need to make the imaginary part converge well. I mean, as good, right? So after this, then, yeah, I can say Control S and save it, and then I can run it already. I already say what I want to run. Then I say go to Analyze All. Right, so then you will start the job, and as you can see on the lower right, it start running pass 2, pass 3. So in each pass, it will try to refine the mesh, and so that to get it more and more accurate, right? And obviously, even up to 8 paths is still not converge, right? But that is okay. Okay, but actually, you see that it converge eventually at 8 paths. How do I know that? I'm going to go to this result. I'm going to right click and say create eigenmode parameter report rectangular plot, right? And then I would say, okay, just plot this free frequency, okay? And I only plot the real part, and I say create a new report. Okay, so I did something wrong. What I want to sweep is the pass. So I'm going to change this to adaptive pass, and then say sweep the past, right? So I'm going to just apply trace. Let me just add to a new report, right? Close it, right? So I'm going to delete the old one. The old one I did it wrong. Right click and then delete, right? And now you look at this one, right? So it has 3 different frequency, right? When it reach past 8. And if I right click, I say marker, add marker. I can click on here. I see the first mode is about 7.4 gigahertz. The second mode is about 8.2 gigahertz. And the third mode is about 8.29, right? But we don't know what it is actually. So what we can do is we can also open the design again, and I'm going to fit all to see everything. I want you to plot the electric field distribution. So I click on this one, right? I click on the vacuum, and then I say right click, plot E field, right? Plot E, magnitude of E, the magnitude of E, okay? And then I just say done. Okay, so I see this E field, okay? Now, this E field a lot small, right? Because it depends on how you activate the source. You go to HFSS, fields, and then go to actually edit sources. Right now I'm using peak electric field. So if you want to, sometimes you see people in their publication, they have very large value. They probably use the joule. They just say, I put 1 joule of energy there, right? So I put it there. I just say, okay. This is the first mode, right? So now the range is very large. I right click this one and try to modify. Okay, for example, I can try to modify using maybe this one, use limit, right? Let's say I do 1E8, right? Then I will see this. Now, obviously I did not do a good design, right? If you base, I can click this rotate and try to rotate this guy around, right? This one basically is a cavity mode, the first eigen mode, right? This is a cavity mode, right? We can look at the second mode. I'm going to look at the HFSS results and no fields, and then at the sources, right? So I will look at the second mode. I put this into 1. I need to make another to 0, and then say apply. Okay, this is also cavity mode, right? This is the second mode of the cavity. Okay, okay, will it be the third mode? I'm going to edit source. Right? Because I did not design this well, I do it arbitrarily, so this is not a good qubit resonator. Okay, so unfortunately, this is also a cavity mode, right? Do you see that? This is the third mode of this cavity, right? So I think the reason was because I have a inductance too small compared to the usually what we have, right? So I need to go back just to not edit source, but change the inductance. That's why you really want to have a variable. So instead of 5 narrow Henry, I'm going to do 12 narrow Henry. Okay, and because of this, I need to rerun the simulation. Right. So basically, what I'm showing you that is that when the inductance is low, right, the lowest mode are all due to the cavity. So you are not going to be get something useful by putting the qubit inside, right? Because the qubit has a very high frequency. Okay. Now, so let's take a look now with this one. Let's first look at the eigenvalue plot. Now it's pretty different, right? I think it's different from before, right? But let's see. I forgot what was before, but let's try to plot it again. This one is the if you look at the field at the source, this is the third mode. Remember, now it becomes the second mode of the cavity before, right? Before the second mode looks like this. How about mode 2 of the whole system? Okay, this is the first mode of the cavity before, right? How about first mode, right? Now you see this. This is the qubit mode. Okay, so now because the qubit have large enough inductance, so it has low frequency. And now let's take a look at this one. For example, I can make this how How about auto? Yeah, auto would be better. And then, actually no, maybe 1E9. Yeah, I think I should use auto, right? For now, it's difficult. So you see that all the energy concentrated here, right? Let's use control equal. I will zoom in, right? And this is where we have the qubit, okay? Right? So all the energy concentrate here. Now, of course, it's difficult to see because I'm plotting the vacuum. We only show the vacuum, right? So let's try to highlight the sapphire. Where's the sapphire? Yeah, this one. And then let's ask it to plot the field on the sapphire. Not this one. Field, plots field, E, magnetic, right? I mean magnitude of E. Okay. Now let me just disable the view of the vacuum. Now you look at this, you see that it has a very strong electric field near the qubit, right? If I try to now use my limit, I use 1E9, what do I get? That's too big, right? 1E10, right? I mean, or just auto, right? You see that near the Josephson junction, right here, it has all the energy here due to this large inductance. Okay, so I'm going to use this as the thing we are going to talk to the Qiskit. Okay, now with this, you see we actually can do it manually. But however, you can use Qiskit Metal. You can copy. You need to Google a little bit. This one I got it from the EPR tutorial, right? You just go to Google pyEPR tutorial. And I forgot where I got it, but I think it's from Dr. Minev, right? It has all these example on GitHub, and one of them should be the pyEPR tutorial. I think it's maybe tutorial notebook, not this one. Example, yeah, pyEPR tutorial 1. I think this is where I got it, right? But after I got it, I did some modification, right? Here, just load the stuff, right? And to show it is working, actually, I want to close this window. Okay, I close this HFSS. And then import pyEPR, right? You can take a look. I will share this with you. And then this is just like some what do you call housekeeping, some function that you can use to calculate how the Josephson energy is related to the inductance. So you can ignore them. Now, most important thing is that now I want to open the file that I already done, right? So this is the project path that I have. Okay, now, and then the point is here, right? I have this project 3D cavity. Actually, I forgot the name, right? So I need to go back. It's called okay, I need to copy the file first. Okay, just now I paused the recording because I want to copy the file to my working directory, and it should be called 3D cavity. No. Okay, yeah, I should call it a 3D cavity. I mean the HFSS project is called 3D cavity Transmon AEDT, right? So then I need to change it 3D cavity Transmon, right? Let me make sure that the spelling is correct, right? So if I run it, looks like it can open, right? And the design name, I will show you why it is that, because when I design it, right, now it call, do you see that? It called this project and it does open the project. This project is 3D cavity underscore Transmon and HFSS design 1. That's how you get it, okay? So you got the file and then you just do some checking. You don't need this actually, but yeah, this is doing Eigenmode, right? And it also get all the object names, right? This is useful for you to double check. The main point is, this is just getting the variable. You see, we define a lot of variable from in the last lecture, right? For the size of the device, we define the setup, and we try to get a mesh, but it does not have because I think it treats as the first time, right? And how many mode we are running? It is 3. Okay. Now we realize that the EPR calculation is very slow if you go to 4 modes. And actually, I don't want to use 3 because of the time, right? Because I know that the lowest mode is the qubit mode, and the second mode is the cavity mode. That is what we want already, right? I will assume no more high order effect. So I'm going to just change the analysis setup to 2 modes only. Okay. So let me save it again. If now I try to read it one more time, then it gives me 2 right here, right? Okay, now this is important. We need to tell you where is the Josephson junction, right? As I told you earlier, okay, we have the variable LJ to define the energy, the inductance, right? So let me double check property, and we look at this. Yeah, we call it LJ, which is correct. And then we also need to tell it where is the rectangle that you have the Josephson junction, right? And that's what we said earlier. So if I go to the model sheet, and then here, rectangle 2, I guess, right? Create rectangle, right? Rectangle 2, fit select. Indeed, this is the one, right? And I can confirm by using this model, right? I can also do control minus. Click here to unselect, control minus. Yeah, so this is indeed the area that I have the Josephson junction, right? So it's called rectangle 2. You can give any name. Okay, I also call it rectangle 2. How about the 9 for integration, right? We have been mentioning we need this 9, and this is called poly 9-1. So I need to rename it poly 9-1. Okay, and then the rest, okay, right? Then I run into problem, right? I spell it wrong. There's no underscore, right? It says that here it claimed that it cannot find poly underscore 9-1, right? So I run it again. So it works. Okay, then let's go ahead to do the analysis. Like what we did for the 2D case, right? So it is going to run it, which was just like what I did earlier manually. It's going to run through the 2 modes with probably converge in 8 passes. Okay, so if we look at here, result, expand it, look at the Eigenmode port. Now this time it only has 2 modes, right? Good. And that's it. And then you will run the EPR. Now let's say ask it to run all this stuff, but as you can see, it also get the results. The first mode is 5.29 gigahertz, right? Second mode is 7.4. Quality factor was very high in the first mode, but relatively low in the second mode. But it's very, very, very high compared to the 2D resonance cavity, right? And this is just some plotting. I won't go into details. You can learn yourself how each passes change the delta frequency, right? We have too many parameters. That's why this is so long, right? Eigenmode versus passes. We can ignore it. And then the statistics. Okay, the point is now we want to do the EPR, right? Energy participation ratio. We already calculate the energy, and we also have nowhere to get the energy at the junction and also in the whole device. Then it is doing this, right? So it finished already. You can see that for mode 0, you have a lot of energy at the junction. I showed you just now, right? We have peak electric field at the junction. And the mode 1 is the cavity mode. You have very few energy there, right? So after we have done this, then we can go ahead to do the cross-Kerr calculation. And it is done here, right? So basically you see that the junction I have put in only change the cavity frequency by 78 kilohertz. This is very low. It's not good enough. But we need to come up with a better design, right? But I just randomly pick one, or maybe my design is not good enough. But overall, the message here is on how to calculate, how to build a 3D cavity and use Qiskit Metal to calculate the cross-Kerr. Okay. Yeah. I think that's it, right? And then the rest in the project, I will request everyone to design a good cavity and also play with the Josephson junction placement, and to see how you can increase the cross-Kerr and at the same time you maintain certain Q. Okay.